everybody, physics kids. This is Mr. Johansson, and we're going over Enigma number 18. And this is gravity and Newton's third law. So we're going to just be doing some ideas on gravity. Now, we've talked about gravity before, and where we've talked about it, we're just talking about things on Earth's surface just falling, and we know their gravitational acceleration is 9.8 meters per second every single second. 9.8 meters per second squared. That's how much it adds to their velocity. But why? Well, with the idea of gravity, all matter attracts all other matter. Now, here I have two 1 kilogram masses. What we want to do is, what is their attraction? And what is their attraction at various distances? So to start off, what is the attraction of two 1 kilogram masses when I place them exactly 1 meter apart? All right. Newton got into this idea, and this is what he came up with, and I think it makes sense. See what you think about it. If I were to, say, supersize myself and double my mass, how much harder is the Earth pulling down on me? Well, first of all, you do realize the reason I have weight at all is because I'm standing on the Earth, and the Earth is pulling me down. Well, why doesn't everything else pull me? Why, when I walk past a school building, why doesn't it pull me a little bit towards it? Why, when I walk past, say, the Intrepid aircraft carrier in New York City, you walk past that, do you feel yourself getting pulled towards that? I don't. I've never seen anybody pull towards that. If I hang a yo-yo off a string, is it going to be deflected towards that a little bit? No, not that I would ever see. So does that mean that thing doesn't have gravity? All mass has gravity. When I walk past a mountain, there's a mountain on that side, nothing on that side. Am I pulled? Do I notice anything? A yo-yo on a string, would it go towards the mountain? Again, no. Is it because the mountain isn't pulling on it? No, it can't be. All mass pulls. So why don't I notice it? Why don't I notice when I walk past a building a little bit of pull towards it? Gravity must be a very weak force. Well, it is. When I hold these masses, even if I hold them close, I don't feel any force pulling them together. Not at all. But when I drop anything, just drop it, I see it pull down tremendously. If you understand what I'm saying, next time you see something fall, or pick up something and drop it right now, you should look at it and go, whoa. And realize that gives you a window on seeing how big the thing under your feet is. It's enormous. That it should be able to take something and pull it down like that. When you walk by a mountain, you don't feel any pull at all, and yet the thing you're standing on pulls something down noticeably. If you have a yo-yo on a string, it pulls it exactly straight down, doesn't it? That's what's pulling on the yo-yo. It's the Earth under our feet, and there must be so much mass there. Takes your breath away. Pretty cool. But how would you ever calculate it? All right. Back to this idea. If I supersize myself, and I now have twice as much matter as is in me, isn't the Earth going to pull on all of that matter? So because I have twice as much of it, isn't it going to pull me down twice as hard? Thus, my weight will be increased by 2. If you agree with me, and it would be smart too, if you agree with me, what we're saying is that force of gravity is proportional to the mass. If you double the mass, the force of gravity will double. Well, what's the other mass involved there? Oh, well, it must be the Earth. What if I double the mass of the Earth? Keep it the same size, but double the mass of the Earth. If I double the mass of the Earth, it'll double my weight, right? If I'm standing on something with twice as much mass, it'll double my weight. If you're standing on Mars, you find you don't have anywhere near the weight you have here. Or the moon, much less weight. See the astronauts galloping around on the moon. They don't weigh nearly as much. Their mass hasn't changed, but the moon is a much smaller body, so it doesn't pull them as much. So what we see is the first mass times the second mass. If you doubled both of them, the force between them would be 4 times as great. Well, now I got to show you an interesting law. We got to talk about the distance between them. And the distance between them brings up a very funny law in physics. Usually I try to show it like this. Let's see if you can see this. I'm going to use a flashlight. I don't know if this will come out on the chalkboard, but I'm going to use a flashlight And I'm going to hold it 2 fingers away from the board, draw a circle around the light. Now I'm going to hold that same flashlight 4 fingers away from the board and draw a circle around that. That's all. Now we just want to talk about it. So look at these 2 circles I've partially drawn on the board. All I want to see is the radius of them. So look at the first radius. Look at the second radius. Second radius, how much bigger is it? It's twice as big. When I moved that twice as far, the radius of the circle, thus the diameter of the circle, became twice the size. Okay, good. If we now compare the area of these circles, how much more area does the little circle, or how much more area does the big circle have than the little? It's not twice. What's the mathematical formula? Area equals 2, equals pi r squared. The area is proportional to the square of the radius. So how much more area does the second circle have? 4 times as much area. If the radius is doubled, well, 2 squared is 4, so it's 4 times as much area. How much less light is hitting any spot? In that, if the same light is spread over 4 times as much area, you realize it's 1/4 the light. So if you double the distance from something, you are getting, if it's light, you're getting 1/4 of the light. Turns out if you have any energy source and you double the distance, or any gravity field, or any field at all, if you double the distance from it, you cut the intensity to 1/4. This is known as the inverse square law. And it's a really important law in physics. It's in everything. This might be the first time you're hearing about it, but we all have been using the inverse square law in physics for a long, long time. So, what we have then, force of gravity is proportional to m1 times m2 divided by the square of the distance, and that gives you the proportions. It'll tell you if you double a mass, you're going to double the force. If you double both masses, you'll quadruple the force. If you double the distance, you'll cut the force in 1/4. Shows you what's going to happen to the force in a lot of conditions, but it doesn't tell you what the force is. For that, you need an equal sign. And to make it an equal sign, you need a constant of proportionality. In other words, what you really need to do, you need to do an experiment. You need to find out how hard these are pulling on each other. Well, Henry Cavendish did an experiment like that to find the density of the Earth. And when you use that experimental data, it gives you the value, and he got it very close, the value of the universal gravitational constant, big G. Now, little g is useful only on this little biofilm on Earth. Way up above the Earth, it's not little g anymore. Way down, it's not little g anymore. Little g is useful for us because it happens to be the gravitational acceleration in almost every situation we find ourselves in. But in terms of the gravity in the universe, it's useless. But big G is the universal gravitational constant, so it applies everywhere. And that number, it's on your reference tables. Look up big G on your reference table. It's 6.67 times 10 to the minus 11. The units are funny here. Newton meters squared per kilogram squared. So what does this really tell us? Well, why don't we do the problem? Here's the problem. What is the force between these two 1 kilogram masses when they're 1 meter apart? Let's do that problem, shall we? All right, so the givens. Mass 1 equals 1 kilogram. Mass 2 equals 1 kilogram. The distance equals 1 meter. Capital G equals 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. And we are looking for the force of gravity between them. Formula, F sub g equals g m1 m2 over d squared. We don't have to mess around with that. S and S, we already are solving it for what we look for. F sub g equals g m1 m2 over d squared. Now, where are you going to mess up? What's going to probably mess with you? The squaring, of course. Any place we have a square, worry about it. That's where we'll mess up. But if you use units carefully, you'll see when you mess up. Anyway, let's sub in. F sub g equals 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times 1 kilogram times 1 kilogram over 1 meter, entire quantity, squared. Check the units first. Well, meters is going to be meters squared. That's going to cancel that meter squared. That kilogram and that kilogram are going to cancel that kilogram squared. So we're ending up with newtons. That's what we want. Wait a second. 6.67 times 10 to the minus 11th times 1 divided by 1. Hey, what's the force between two 1 kilogram masses? Do you see it now? Pretty funny. The force between two 1 kilogram masses is 6.67 times 10 to the minus 11th newtons. 6.67 times 10 to the minus 11th. Let me write that out for you. .67. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Whoa! So 0.0000000000067 newtons. That's how much force is between these two 1 kilogram masses when they're 1 meter apart. Hey, what if they're only half a meter apart? They're only half a meter apart. What would we multiply that by? Well, what would you do? Is the gravity going up or down if they're closer? Good, gravity's going up. We use the inverse square law, right? So if we've gotten the distance in half, did the gravity double? No, it's 4 times as much. You can put it right back in the formula if you want to see how that works, but it's 4 times as much. What if we make the distance twice as far? Well, this number would be 1/4 as much. So it's going to obey that inverse square law. So that is universal gravitational formula. You can use it to solve all sorts of useful things. There's a couple example problems on this paper. Why don't you give those a try? Next time, we'll cover Newton's third law. Hey, thanks for watching.